Hi students, I'm going to talk a little bit about how to solve the problems on the exam right now. I'm going to go through one at a time, each one with its own little video, so that you can kind of see in a very slow, leisurely way how to solve these problems. This first problem is to basically find the Thevenin equivalents of a variety of simple circuits and to match the ones that are the same, depending on which version of the exam you got a different one to match to. So we'll start from the beginning. I'm going to zoom in here on this one, and we want to see that it's in fact already a Thevenin equivalent. And a Thevenin equivalent means to find a value of the Thevenin resistance R Thevenin and a Thevenin voltage V Thevenin for each one. So I will just write those down on this first one. We have here R Thevenin is equal to 1K and V Thevenin is equal to 10 volts. Going on to the next one, we've got a 10 volt power supply. This is a voltage source. And that means that it is going to keep a constant voltage between this point and this point, regardless of what else is attached. So if I'm looking at the Thevenin equivalent voltage, which is to the open circuit voltage between this point and this point, it's going to be the same as the voltage between this point and this point. So the Thevenin voltage is simply 10 volts. On the other hand, the Thevenin resistance is basically going to be the resistance that one would see looking back from the output through the resistors back through the other terminal. And because this voltage source right here is in parallel with this resistance right here, the resistance itself does not matter because the voltage is maintained to be the same between those 2 points. So in this case, the Thevenin resistance is also 1K, just this one resistor that is in series. Moving to the third one, we have the Thevenin voltage is going to be the voltage between this point and this point when there's nothing attached to the circuit. And so that means that the voltage that is produced by the voltage source is going to drop as it sends current through this resistor here and this resistor here. Those two resistors are in series and they are the same value, and for that reason I know that the Thevenin voltage is basically equal to half 10 volts or 5 volts. The Thevenin resistance, on the other hand, is going to be what I would see looking back through the circuit from the output, and I can see that there is a 2K in parallel with another 2K because I'm connecting that in series with a voltage source which has itself no resistance. So it's 2K parallel with 2K, and that is equal to 1K. That's our Thevenin. Going down now to circuit D, we see a 10 milliamp current source. So this is a difference between the ones that we've done previously. A current source provides a fixed current through whatever it's attached to. If nothing is attached to the output, then the current is all going to flow through this 1K resistor, and that's going to be 10 milliamps when nothing is attached. And so that means the voltage that is seen between this point and this point is the same as the voltage between this point and this point because there is no current in this resistor here. And therefore the Thevenin voltage is given by 10 milliamps times 1K, or 10 volts. On the other hand, the Thevenin resistance is different than it was previously because this current source has effectively an infinite resistance, and so the Thevenin resistance is going to be this 1K in series with the other 1K, or 2K, and that's equal to the Thevenin resistance. This is an important distinction between how current sources act and how voltage sources act. Going on to circuit E, we again have a current source. We again have a 1K and a 1K. The main difference is where is the 1K. Here the 1K is right in front of the current source. Here the 1K is out on the output of the circuit. So the Thevenin voltage is basically the same as it was before because this puts 10 milliamps through the entire circuit. So 10 milliamps is still being sent through this 1K, so the Thevenin voltage is the same as it was before, 10 milliamps times 1K, which is equal to 10 volts. On the other hand, the Thevenin resistance is now, looking back this way, going to be a 1K in parallel with what would be a very large resistance. So it's 1K in parallel with basically an infinite resistance, and this basically gives a 1K for the Thevenin resistance. Notice that that is different from this one over here. So now we go into a slightly more complicated problem. I have a 1K in parallel, as I did before, with the current source. I have a 2K now, but it's not in parallel with 1K. It actually is on the other side of this upper 1K. So what we will need to do is to take a little more care as to what the Thevenin voltage would be. So it turns out the easiest way to solve this problem is to go through the procedure by calculating the short circuit current. So the short circuit current is what you get if you connect a wire between these points and you want to calculate what current would flow through that wire. Notice that this wire shorts out this 2K resistor here. So this 2K resistor is essentially taken out of the circuit. So this 10 milliamps then is going to split that way and that way. It's going to divide in two. So I short circuit is going to be equal to 5 milliamps because I've got the same resistance going to the other side of the current source along both paths. That means I can use this, and when I calculate what the Thevenin resistance is, I can then calculate the Thevenin voltage. So if I remove this short circuit current, then I can calculate the Thevenin resistance by imagining putting an ohm meter between that point and assuming this is an open circuit. Then I would have this 2K in parallel with the series combination of this 1K and this 1K. So our Thevenin is going to be 2K in parallel with the combination of 1K plus 1K, which is of course 2K. And 2K in parallel with 2K is just 1K. So now I have the Thevenin resistance, I have the short circuit current, and the Thevenin voltage is equal to R Thevenin times I short circuit, which is equal to 1K times 5 milliamps, or 5 volts. That's the trickiest one of the bunch. 10 volts and 2 4Ks. This is basically the same as another one that we've seen, except now I've got 4Ks instead of 2Ks. So I have the following. I have that the Thevenin voltage is basically just 5 volts as it was before because I have two resistors that are the same. But the Thevenin resistance is going to be 4K in parallel with 4K, and that is 2K. Over here, a 5 milliamp current source dropped across a 1K resistor. This is really the same circuit as this one over here, but now instead of 10 milliamps, I only have 5 milliamps. So the same argument pretty much applies. I can get the Thevenin voltage by looking at the open circuit voltage, which is the same as the voltage drop across this 1K. So V Thevenin is equal to 5 milliamps times 1K, which is equal to 5 volts. And looking back through this way, I can see that my R Thevenin is 1K plus 1K, which is 2K. And the last one looks almost the same as one we had earlier. Remember, this resistor in series with a current source does not have any effect because this is like a 1K in series with an infinite resistance. So the 5 milliamps goes through 2K. The Thevenin voltage is equal to 5 milliamps times 2K, which is 10 volts. And the Thevenin resistance is equal to 2K. So that's the whole set. Now we can pick out which ones are the same. So what we have is that 1K and 10 volts. So that one there, 1K and 10 volts, that one there, 1K and 10 volts, that one there are the same. The other ones are 10 volts and 2K. So we look around for 10 volts and 2K. There's a 10 volt and 2K. So here and here are the same. I have a 5 volt and a 1K, so that's going to be 5 volts and 1K, 5 volts and 1K. And then finally, we've got 5 volts and 2K, 5 volts and 2K. So those are the ones that are all the same.